Hello, everyone. Welcome to the GOCC. This week we have Rowan speaking about skeletal complexes. But before I introduce him properly, I would like to remind everyone about our community statement. At the GOCC, we just want to remind everyone that first, we are all learning. Second, everyone has something to contribute. And finally, no one has all the answers. So if you have any questions during the talk, feel free to address them to the speaker, or if you're not comfortable doing that, go ahead and put them in the chat and one of the organizers will make sure to do so. But with that said, it is my pleasure to introduce Rowan Rollins talking about the topology of the complements of skeletons. Take it away, Rowan.
All right, thank you. Let me pull the share screen back up again then. Okay, well, hello everyone. Thank you for that introduction, and yeah, thanks for the invitation to speak today. Yeah, I've been looking forward to it. So, yep, like you mentioned, today I will be talking about the topology of complements of skeletons. So, just to note, this talk is based on a preprint on the archive with the same name. If you want to check for further details, search that up. All right, so let's start in the usual way by defining some of the things we'll be considering. So the main kind of object we'll be studying today is something called a polytopal complex. So a polytopal complex is a collection of polytopes in Euclidean space Rn for some dimension with a couple of properties. First up, for every polytope in the collection, all of the faces of that polytope are also in the collection. So collections like closed undertaking faces. And secondly, for any two polytopes in the collection, their intersection is a face of each of them, or possibly the empty face. So this is just saying that polytopes intersect nicely. They kind of glued along their faces and we don't have weird overlaps. So here are some examples of polytopal complexes. We've got this one built out of triangles here. You can have one built out of cubes. This is a three-dimensional one. And this is like a more generic one over on the right here. These pictures kind of illustrate some special cases of polytopal complexes. So for example, if every polytope in the collection is a simplex, then this is also called a simplicial complex. If I can spell that right, here we go. So simplicial complexes are probably the most famous kind of polytopal complex. You are probably most likely to have come across this kind of complex before. Actually, for most of today's talk, I'll say the first 2/3 of the talk, if you only want to think about simplicial complexes, then that's totally fine. All of these results say interesting things, I think, about simplicial complexes. So yeah, if that's something you're more comfortable with, yeah, think about simplicial complexes. There is another family of polytopal complexes that I am personally much more interested in, though, which is called a cubical complex. And as you might guess from the name, a cubical complex is just a polytopal complex where every face is a cube. When I say cube, I mean cube of any dimension. So this is including line segments and squares and 5-dimensional hypercubes. So yeah, dimension agnostic here, but yeah, I want every face to be a cube, then it's called a cubical complex. And then this third picture here is just like a picture of more generic arbitrary polytopal complex, just to show that like the faces don't all have to be the same. You can have like more weird, yeah, arbitrary complexes. All right, so those are the basic objects we'll be looking at. Now let's get on to one of the words in the title of this talk, and let's talk about skeletons and co-skeletons. All right, so if you have a polytopal complex, its k-skeleton for some integer k is defined to be the collection of faces of that polytopal complex whose dimension is less than or equal to k. So here are some pictures, for example, down at the bottom. If x is this complex we had on the previous slide, its one skeleton looks like this. It's the collection of faces of dimension 1 and lower, so 1 and 0, and the empty face if you count that as a face. This is also sometimes called the graph of the complex. If you just have the vertices and edges, yeah, you get that picture here. So that is the k-skeleton. But instead of talking about the k-skeleton today, I'm going to talk mainly about the complement of the k-skeleton. So I'm going to define something called the k-co-skeleton to be, well, the complement of the k-skeleton. It is the collection of faces of the complex whose dimension is greater than k. So for example, this picture here shows the 0th co-skeleton is the collection of faces of dimension greater than 0. So all of the faces except for the vertices and the empty set. You care about the empty set. So it's just this complex here, but with all of the vertices deleted. Yeah, I want to think of this topologically as well. So think of this as a topological space with all of the points that are the vertices removed from it. Right, so the K-skeleton of a complex is something that's very widely studied. It's a very common thing to define and consider for complexes. Like if you pick up any algebraic topology textbook, it will probably mention K-skeletons at some point. But as far as I'm aware, the complement of the K-skeleton, the K-co-skeleton, hasn't really been considered much at all. Like it might come up in some obscure papers, but I couldn't find any like significant study about it. It's similar to some ideas that come up around Poincare duality, but yeah, otherwise, I think this project might be the first project to like really focus in on the K-co-skeleton as an object to study. All right, let's talk about some other useful features of polytopic complexes as well before we get into like the new stuff. So I'm going to define two things. I'm going to define the star and the link of a face in a polytopic complex. So if we have a polytopic complex and a face of that complex, then the star of that face is defined to be the set of faces of the complex that contain the given face sigma. So for example, if this is our complex here and sigma is this vertex on the right, then the star of that vertex is the collection of these 3 triangles and 4 edges that contain that vertex and also the vertex itself. So notice that even though X is a polytopic complex, the star generally isn't a polytopic complex. So this is like one downside of studying these things is we have to leave the world of polytopic complexes in order to study them. But yeah, topologically, it's still something you can consider. Right, so that is the star of sigma. The link of sigma is pretty similar. It is the set of faces of the polytopic complex that contain sigma, but aren't equal to sigma. So like exactly the same as the star, but we just delete the face sigma itself. So here's a picture of the link of this vertex. It's the same as the star, except the vertex itself has been removed from the picture. If you're familiar with simplicial complexes, you might notice that this definition is a little bit different from the usual definition of a link of a face. If you think of this set of faces as a poset ordered by inclusion, then as a poset that is isomorphic to the more traditional link of a face if you remove the empty face. Also, it is homotopy equivalent to the usual link as well. So this is like a slightly more topological version of the more traditional link of a face. Okay, yeah, topologically, the reason you might care about a link is it gives you some slightly more combinatorial notion of an open neighborhood of a point. So the link of a vertex here, yeah, this vertex link is, yeah, it is an open neighborhood of this point here with the points kind of punctured out of it. So yeah, this link is kind of like a bridge between combinatorics and topology in that sense. Right, now that I've mentioned topology, let's actually get into some of the more topological tools we'll be using. Actually, the topological tool we'll be using homology as a topological perspective on these spaces. Right, so because this is a graduate colloquium for combinatorialists and not like tenured professor colloquium on topology, I will give you like a quick summary, like recap of what homology is, just in case it's been a while since you've seen it or you haven't seen it before. This will be like a very quick introduction, but here we go. So if you have a topological space, you can define something called the ith homology group of that space for any integer I, which will be, sometimes it's a group, but today it's going to be a vector space that we assign to our topological space, and it's denoted like this, tilde h subscript I of S. And this vector space, or the dimension of this vector space is kind of counts the number of I-dimensional holes in the space. So for example, if the topological space is a coffee mug, then the handle of that mug forms like a one-dimensional hole in that space. Like you could pass a one-dimensional piece of string through the handle and tie it on, and you couldn't take the string off. And that handle is kind of the only place that such a hole appears. And so the degree 1 homology of a coffee mug is a one-dimensional vector space because there's one-dimensional hole. Right, that was a very, very quick introduction to homology. Yeah, that's hopefully enough of an idea to work with today. There's a lot you can do with homology, but today, kind of the one thing that we will use about homology is this theorem here called the Meyer-Vittorius theorem, which tells you some relationship between homologies of various spaces. So in particular, if you have A and B being subspaces of a topological space with like some fairly mild conditions on what kind of subspaces you consider, then we have something called the Meyer-Vittorius exact sequence, which tells us some relationship between the homology of the intersection and the union and the homologies of just A and B themselves. So this is something called an exact sequence, which means that we've got these vector spaces and then linear maps between them with the property that the image of each of the maps is equal to the kernel of the next map along in the sequence. So for example, the image of this map equals the kernel of this map, and so on for the rest of the sequence. And so the way this sequence works is we've got the intersection homology here, then the direct sum of the homologies, and then the union. And then we kind of loop back to the start with the intersection again, except this time the degree of the homology is I-1, it goes down by 1. So then we kind of loop through going in this pattern, intersection, direct sum, union, intersection, direct sum, union, and so on with the degree of the homology going down by 1 each step. Okay, so that is the Meyer-Vittorius exact sequence that we'll be using today. All right. Okay, so those are all of the definitions and tools that we'll be using today. Let's actually apply them and see what kind of results we can get. So in particular, we're going to take this Meyer-Vittorius exact sequence and apply it to co-skeletons, and we will end up with an exact sequence that looks like this. So if you have a d-dimensional polytopic complex and you pick some value of k in this range, then you can get an exact sequence that looks like this. We've got the direct sum of homologies of links of k-dimensional faces, and then the homology of the kth co-skeleton, then the homology of the k-1th co-skeleton, and then the sequence loops back again, back to the start with the degree going down by 1 at each time you go through the loop, just like the Meyer-Vittorius theorem. All right, so the idea for proving this is like we're going to take the Meyer-Vittorius theorem and apply it. So if we're going to apply the Meyer-Vittorius theorem, we need to pick these subspaces A and B to apply it to. And specifically, the sets we'll choose will be A will be the kth co-skeleton of our polytopic complex, and B will be a disjoint union of open neighborhoods of the k-dimensional faces. So to be a little bit more precise there, the way that we'll set up these open neighborhoods of the faces is we will take something called the barycentric subdivision of the polytopic complex. So this is a subdivision, meaning like a polytopic complex with like smaller polytopes than the original complex. And the barycentric subdivision has a nice property that for every face of the original complex, you get a vertex of the barycentric subdivision. And so for each face of the original complex, or each k-dimensional face of the original complex, we'll take the vertex of the barycentric subdivision corresponding to that face and consider the open star of that vertex. And if we take the disjoint union of that over all k-dimensional faces, we will end up with a picture that looks something like this. So this is the case where k equals 0. So we're taking stars of actually the vertices of the complex this time. And yeah, as you can see in this picture, we'll end up with a bunch of open neighborhoods of all of the vertices. Right, so that was a bit of a hand-wavy explanation, but yeah, so that is the construction we'll be working with. All right, so to apply the Meyer-Vittorius theorem, we don't just need A and B, we also need to consider the union and intersection of A and B as well. So let's think about those for a moment. For the union of A and B, let's think about that starting with the set A. We've got the collection of all faces of dimension greater than k. So that's the definition of the kth co-skeleton. But then when we take the union with B as well, we're kind of throwing in the k-dimensional faces too. Yeah, we're taking in each k-dimensional face and a little neighborhood around it. So when we add that to this union, we will end up with the faces of dimension k and greater. The way that we set up this union guarantees that the faces of smaller dimensions still are left out. So we'll end up with faces of dimension k and greater, which is the set of faces of dimension greater than or equal to k minus 1, which is exactly the k minus 1th co-skeleton. Okay, so that's the union. For the intersection of these two spaces, let's start by thinking about B first. This time, we've got a disjoint union of open neighborhoods of all of the k-dimensional faces. But then when we intersect that with A as well, we're also kind of deleting the k-dimensional faces from that picture. So we'll end up with a union of open neighborhoods of those faces, but with the faces themselves deleted, which sounds a lot like how we defined the link a couple of slides ago. It's not exactly the same as the link we defined before. The open neighborhoods we're using are slightly smaller than the ones in the definition of the link, but hopefully it's not too hard to believe that these two ideas will be homotopy equivalent, if not actually equal. So yeah, that's why I put this symbol here instead of an equal sign. So, all right, so there we go. That is all of the ingredients we need to put into the Mayer-Vittoris theorem. Let's see what happens when we do that. So I've just copied down what we figured out about all these sets again, and this is a copy of the Mayer-Vittoris exact sequence. Let's see what happens when we plug it in. So first up, we've got the intersection of A and B. So that was the disjoint union of the links. Now, when you take homology of a disjoint union, you can turn that into a direct sum of the homologies of the individual pieces. And so this ends up being the direct sum of the homologies of the links. This works in all degrees except for degree 0. Degree 0 is much more fiddly and annoying to deal with in this theorem than all of the other degrees. So I am just going to ignore degree 0 for today, so we don't have to worry about the pages of details to justify why that still works. But apart from degree 0, this is what we get for the intersection. All right, then next up, we've got a direct sum of homology of A and B. Okay, well, the homology of A is the homology of the co-skeleton. That's just plugging that in directly. For the homology of B, we've got a homology of a disjoint union of open stars. So again, a homology of a disjoint union becomes a direct sum of homologies, but the star of any non-empty face in a polytopic complex is always contractible. So its homology is always 0. And so this homology of B term here is a direct sum of just a bunch of zeros. And so this whole term here disappears. Again, this doesn't work in degree 0, but let's ignore that. Okay, and then finally, we've got the homology of A union B, which is exactly the homology of the k minus 1th co-skeleton. And so there we go. We've plugged all the plugged in all of these things into the Mayer-Vittoris theorem, which gives us the exact sequence that we're looking for. So again, modular details about degree 0 and a couple of other details. That's how this theorem works. All right, before we move on, let's, I wanted to take a look at an example of this theorem just to convince you that, that it does actually make sense. So let's take a look at this example here. We're going to take X to be the polytopic complex that is the boundary of an octahedron, just to have something concrete to work with. And we're going to take K equals 0. Right, so yeah, X is the boundary of the octahedron. It's like a hollow thing. It's not filled in on the middle, just to make that clear. All right, so there's a couple of homologies we need to consider. So let's think about these individual pieces and what they look like. First up, the link of the k-dimensional faces, or link of the 0-dimensional faces here. We need to consider the links of the vertices. Right, so by symmetry, all of the vertices can look the same. So I'll just draw a picture of one of the vertex links. It looks something like this, so like a square, but with a hole punctured in the middle where we delete the vertex. Okay, so that's the link of the vertex. Next up, let's think about the kth co-skeleton, or the 0th co-skeleton in this case. So that is this boundary of an octahedron, or like this sphere, but with the 6 vertices of the octahedron deleted. So this is a sphere minus 6 points. 2 sphere minus 6 points. Right, then lastly, we've got the k minus 1th co-skeleton, or the minus 1th co-skeleton. So this is X, but with the faces of dimension -1 deleted. So we're taking X and deleting the empty face. Topologically, that doesn't make any difference at all. So the -1th co-skeleton topologically is just the same as the whole complex itself. And in this case, the complex is a sphere. Okay, so now I think we're ready to plug those into this exact sequence and check that it is actually exact. So most of the terms in this exact sequence are 0 until we get to this term here, which is the first non-zero term in the sequence. We're looking at the degree 2 homology of the -1th co-skeleton. So the degree 2 homology of a 2-dimensional sphere. A 2-dimensional sphere has one 2-dimensional hole, like that whole sphere itself is the 2-dimensional hole. And so this homology is a 1-dimensional vector space. Next up, the degree 1 homology of the links. Each link is a punctured disk. And so that you can have a deformation retraction from that to a circle. And so yeah, essentially it's got one dimensional hole. Okay, so for each vertex, we get a 1-dimensional vector space here, and there are 6 vertices. So this whole space here is a 6-dimensional vector space. Okay, next up, we've got the degree 1 homology of the 0th co-skeleton. So the degree 1 homology of this sphere punctured 6 times. If you take that sphere and look at one of the puncture holes, you can kind of stretch out that hole and stretch the sphere into a disc shape with 5 remaining puncture holes. And so, yeah, this space is homotopy equivalent to a disk punctured 5 times. So that's 5 1-dimensional holes. So this vector space is a 5-dimensional vector space. All right. From here on, the calculations get a bit easier. The degree 1 homology of the -1th co-skeleton is the degree 1 homology of a 2-dimensional sphere. 2D sphere has no 1-dimensional holes, and so this space here is just 0. And then we get onto some degree 0 homologies. Now the degree 0 homology of any connected space is always 0. And so because all of the spaces we're considering are connected, all of these homologies are just 0. And there we go. There is our claimed exact sequence. And the spaces we got, this R1 and R6 and R5, they can form an exact sequence. I haven't told you what the maps are, so you kind of have to trust that the maps work out, but assuming they do, these dimensions are suitable dimensions for an exact sequence. So yeah, looks like the theorem does actually work in this case. All right, one thing to observe about this exact sequence is that most of the terms ended up being 0. There were only 3 non-zero terms in this whole exact sequence. And it turns out this is an example of a slightly more general phenomenon, which we will talk about next. So next, let's take a look at some theorem applications of this exact sequence. So we are going to consider a family of complexes called Cohen-Macaulay complexes. So let's define those. Suppose you've got a d-dimensional polytopic complex X. We say that this complex is Cohen-Macaulay if, first of all, it is pure, meaning that all of the maximal faces have the same dimension. Don't worry about that bit of the definition so much today. The more interesting bit today is this condition here, that the ith homology of the link of any face is always 0. And that's for any face, including the empty face, and all values of I less than d minus dimension of sigma minus 1. So this dimension here kind of equals the dimension of the link of sigma, since we assumed pureness. All right, so Cohen-Macaulay polytopic complexes actually a fairly broad family of complexes. So for example, every sphere is Cohen-Macaulay. If you're familiar with simplicial complexes, you might have come across this definition before. Also, if you're familiar with algebra, then you might have heard of Cohen-Macaulay rings as well. The connection there is a simplicial complex is Cohen-Macaulay if and only if its Stanley-Reasoner ring is a Cohen-Macaulay ring. So yeah, this Cohen-Macaulayness condition was first considered from the algebra world, but it turns out that there's this much more topological interpretation of it as well, for simplicial complexes at least, and you can also define it for general polytopic complexes too.
Just to extend on that, so
Please, yeah.
this polytopic definition of Cohen-Macaulay doesn't have any algebra connections that you're aware of out if your complex isn't simplicial?
As far as I'm aware, that's right, yeah.
Okay.
Yeah, for cubical complexes, there have been some attempts at trying to define some equivalent of a Stanley-Reasoner ring. I'm not aware of any especially successful attempts at that. Like there are some kind of algebraic structures people have defined that have some similar properties to Stanley-Reasoner rings, but yeah, even for cubical complexes, I don't think that there's any well understood algebraic interpretation of this definition. And for general polytopic complexes, yeah, I guess there's nothing known.
Thanks.
Good question, yeah. All right, so yeah, Cohen-Macaulay complexes essentially are something that lots of people like to study from a bunch of different perspectives. Today, let's think about how they interact with co-skeletons. So we end up with this proposition here characterizing when a complex is Cohen-Macaulay. So this proposition says that a polytopic complex is Cohen-Macaulay if and only if it is pure. Again, don't worry about that bit so much. And the ith homology of the kth co-skeleton is 0 for all values of k and all I less than d minus k minus 1. So this proposition here, I think, looks pretty similar to the definition of Cohen-Macaulayness in terms of links. Like we kind of just replaced the word link with the co-skeleton in this definition. And yeah, haven't really changed anything else. So I think, yeah, from my perspective, this proposition kind of gives some kind of intuition for saying that the co-skeletons kind of encode the information of the links, but in a more global way. So they take like the local information of links and represent it globally somehow. Like that's not a very rigorous statement at all, but that's, I think, maybe a good intuition to have about co-skeletons. But let's see where this proposition is true. Where we go on. It's not hard to prove now that we have this big exact sequence. So yeah, we're kind of just going to apply this to the exact sequence and see what it says. So if we're trying to prove this if and only if statement, we've got two directions to prove. So first of all, let's assume that X is Cohen-Macaulay. Then by definition, this means that the ith homology of links is always 0 for certain values of I, which tells us that this term here of our exact sequence is 0. Now, whenever you have a 0 in an exact sequence, that actually tells you quite a lot about the terms around it. So because this space here is 0, that means that this map is 0, and so the image of this map is 0. Then by the definition of exactness, that means that the kernel of this next map is 0, which means that that map is injective. Okay, so we get an injection from this homology to this homology here. The homology of the kth co-skeleton injects into the homology of the k-1th co-skeleton. If you consider varying values of k, now we get this chain of injections here from the kth co-skeleton to the k-1th to the k-2th co-skeleton, k-2nd co-skeleton. Anyway, and so on until you get to the -1th co-skeleton of X. Now we noticed on a couple of slides ago that the -1th co-skeleton of any space is just topologically equal to that space. So this term here is just the ith homology of X. But another name for X is that it is also the link of the empty face of the polytopic complex. It's the collection of all faces of the complex that contain the empty face, so that is all of the faces. And so this term here equals the ith homology of the link of the empty face, and by the definition of Cohen-Macaulayness, that link has to be 0. All right, so now we have this whole chain of spaces all injecting into 0, and so all of the spaces in this chain must also be 0. And so we've proved one direction of this statement. The other direction is even easier. If we start by assuming that all of these ith homologies of co-skeletons are 0, then let's take a look at our exact sequence again. Here we're kind of shifting the window that we're looking at the sequence by one step to the left. And we notice that this term is 0 kind of by assumption. This term is also 0 because the indices still fit within the ranges that we're considering. And so we've surrounded this term in the middle here by zeros. And by similar logic to before, since this space is 0, this map is injective. And so this space must inject into 0. And so it must also be 0. And so the links of all of the faces must have 0 homology for the right range of I. And so X is Cohen-Macaulay. There we go. So we have that result there characterizing Cohen-Macaulay spaces in terms of the homologies of the kth co-skeletons. It turns out we can actually do something similar for not just Cohen-Macaulay complexes, but a couple of other families of complexes as well. So we can get some pretty similar characterizations of a polytopic complex being R-Larray or being an S-stacked ball in terms of the ith homology of the kth co-skeleton being 0 for some range of values of k and I. So again, I think this justifies why you might want to consider kth co-skeletons and why they kind of somehow represent, or they give you like a global version of the local information of the space. So I'm not telling you what R-Larray or S-stacked mean. I'm just like putting these words here to motivate why why these kind of results might be something you care about. There's also this other theorem down below, which isn't quite as similar as the others, but is still, we can characterize this T-neighborly property in terms of homology of a co-skeleton not being 0 this time, but having the right non-zero dimension in some degree. So yeah, essentially we can characterize a bunch of topological properties in terms of homologies of co-skeletons. Okay. So next up, I want to take a bit of a detour and let's leave behind co-skeletons for a minute. We'll get back to them eventually, but next up, I want to talk about cubical complexes in particular. So yeah, I think cubical complexes are something I'm particularly interested in, and kind of the reason why this whole project came about. I discovered something about co-skeletons of cubical complexes and then realized that it applied a bit more generally. So yeah, cubes are really the reason why this project exists. So let's talk about cubical complexes. Let's talk about hyperplanes. Before I tell you what a hyperplane is, though, I need to tell you what a midcube is. So suppose you have some cube, an r-dimensional cube, and to make it concrete, let's pick the coordinates so that this is the unit cube where all coordinates range between 0 and 1. Then a midcube of this cube is a subspace where you set one of the coordinates equal to 1/2 for some like fixed coordinate. So for example, if you have a 3-dimensional cube, it has 3 midcubes where you set either x equals 1/2 or y equals 1/2 or z equals 1/2. Okay, so that's the midcubes of a cube. Let's broaden this to cubical complexes then. So if you have a cubical complex, then a hyperplane in that cubical complex is like a polytopic complex made out of the midcubes of that complex. So for example, if this is the cubical complex we're looking at, then it has these 6 hyperplanes shown here. The word hyperplane does mean something else already in math. This is one of those cases where there's just one word with 2 different meanings, I think. I guess some similarities between this hyperplane and the more traditional meaning of hyperplane, but I think it's best if you just forget that hyperplane means something else and just think of this as an entirely new definition here. So yeah, sorry about that. This is just like the standard word that everyone uses, so I kind of stuck with it. But yeah, most people who study cubical complexes do consider hyperplanes, that they are like a very useful tool in studying cubical complexes. I'd say kind of similar to the role that links play in simplicial complexes. Like links are a really useful tool for a simplicial complex. I think hyperplanes are kind of similarly the combinatorial thing that you'd like to consider for a cubical complex. So the the properties of hyperplanes that I am especially interested in is asking when do the hyperplanes intersect each other. So in particular, I've defined something called a crossing complex for a cubical complex. So if you have a cubical complex, its crossing complex is going to be a simplicial complex that tells you something about the intersection pattern of the hyperplanes. So if I'm defining a simplicial complex, I need to tell you what the vertices and faces of that simplicial complex are. So the vertices of this crossing complex will be the hyperplanes of the cubical complex. So we'll have one vertex for each hyperplane. And then for the faces, any set of hyperplanes forms a face if the intersection of those hyperplanes is non-empty in the cubical complex. So for example, if we're looking at this cubical complex here, its crossing complex looks like this. So for example, the face 1, 2, 4, the set 1, 2, 4 is a face of this crossing complex because the hyperplanes 1 and 2 and 4 of this cubical complex all intersect each other in the middle of this three-dimensional cube on the left here. And similarly for all the other faces of this complex, for each face of this complex, you can check the hyperplanes of the cubical complex intersect each other. Okay. So the crossing complex is something you could define for any cubical complex, or any nicely behaved cubical complex at least. But there is one family of cubical complexes where crossing complexes and hyperplanes work especially nicely. And that is a family called cat-0 cubical complexes. So let me give you the definition for these as well. This definition is it's got some heavy details in it that I'm going to kind of skim over today, but here's the definition. So a cubical complex X is called cat-0 if topologically the complex is simply connected. And then there's also this combinatorial condition that the link of every vertex is isomorphic as a poset to a flag simplicial complex. Okay, so in a cubical complex, vertex links are always isomorphic to simplicial complexes, but for cat-0 ones, we're requiring that those simplicial complexes are flag, whatever that means. I mean, specifically, that means that the cliques in the graph of that simplicial complex are faces of the simplicial complex. Okay, lots of details in that definition. Don't worry about the details. This is just like some family of cubical complexes that behave really nicely. So the reason for the name cat-0 is that the cat bit is the initials of some metric space theorists. I think it's Cartan, Alexandrov, and Topology. I might have got that wrong, but yeah, the reason why cat-0 spaces are a thing that people consider is because of metric space theory. This was first considered from the perspective of metric spaces, because there's an equivalent statement of this definition that, so the equivalent version is that X is simply connected and the curvature at every point is non-positive. Again, whatever that means, like I'm not a metric space theorist, so this isn't really my area, but yeah, metric space theorists care a lot about cat-0 spaces for whatever metric space reasons they care about. There are a bunch of other nice properties about cat-0 spaces that are more relevant today, though. So for example, every cat-0 space and also a cat-0 cubical complex is not just simply connected, it's actually contractible topologically. So like really simple from a topological perspective. Also, in a cat-0 cubical complex, the hyperplanes are also cat-0 cubical complexes, and actually every non-empty intersection of hyperplanes is also a cat-0 cubical complex. So it's kind of like cat-0 all the way down. And also, if you've got a cat-0 cubical complex, the hyperplanes of that complex are two-sided. They split the complex into two halves, which is not something that happens in general for cubical complexes. So for example, if the cubical complex is like if you take a 1/n strip of squares and glue the ends together into like a band, then for example, this hyperplane doesn't split the complex into two pieces. Like if you cut along that hyperplane, you'll still have one piece of the complex left over. So the two sides of that hyperplane are kind of like the same piece. But for cat-0 things, that doesn't happen. Every hyperplane actually splits the complex into two halves.
Out of curiosity,
Mhm.
Is that not covered? So would this be true of all simply connected spaces?
Good question. Yeah, no. Spheres, for example,
Right.
can have really weird hyperplanes as well. Yeah, like if you're just working in the world of cubical polytopes, so like a sphere where
Mhm.
all of the faces are cubes, then you can have such a thing that only has one hyperplane because the hyperplane intersects itself all over the place. And so then like to talk about the sides of that hyperplane doesn't even make sense because it crosses over itself all over the place.
Okay.
But again,
Excellent.
for cat zero things, that doesn't happen. You don't get self-intersecting hyperplanes.
Excellent. Thank you.
In general, yeah, hyperplanes can do really weird things, but for cat zero things, they're really nice. Yeah, good question. Oh yeah, one other thing I wanted to mention here, cat zero cubical complexes aren't just studied by metric space theorists, also group theorists care about them a lot. There's certain families of groups that have natural actions on cat zero cubical complexes. And so studying like the combinatorics or topology of a cat zero space can tell you useful information about the group that acts on it. So that's another reason why people care about cat zero cubical complexes. All right, so I said that that hyperplanes and crossing complexes work especially well for cat zero spaces. Here's an example of some facts that are true about crossing complexes for cat zero cubical complexes. Like I won't talk about these at all really today. This is like beyond the scope of this project, but just to mention some interesting facts or connections between crossing complexes and cat zero cubical complexes. Like for example, the F polynomial of the cubical complex has a strong relationship with the F polynomial of its crossing complex. The cubical complex and its crossing complex share a bunch of combinatorial properties. Hyperplanes of a cubical or a cat zero cubical complex correspond to links in the crossing complex. There's just a lot of interesting connections between cat zero cubical complexes and their crossing complexes. Let's see a more relevant one today though. So let's finally bring co-skeletons back into this picture. So this lemma here says that if we have a cat zero cubical complex, then the kth co-skeleton of that cubical complex is homotopy equivalent to the k-1th co-skeleton of its crossing complex. I think this is kind of a surprising result. We're saying that this kth co-skeleton of this cubical space is homotopy equivalent to something about a simplicial complex. A priori, it doesn't seem like there should be much reason why these should have any kind of similarity topologically, especially since a cat zero cubical complex is always contractible, but its crossing complex can be, actually it can be any flag simplicial complex, so it can have pretty much any well-behaved homotopy type. So yeah, I think this result is kind of surprising. Unfortunately, I can't really explain why this is true. It requires a lot more like details and terminology that we don't really have time for today, but I can give you an idea for a special case of this lemma, which is the case where k equals 0. So if k equals 0, this lemma says that the 0th co-skeleton of the cat zero cubical complex is homotopy equivalent to the -1th co-skeleton of the crossing complex, which is just that crossing complex itself topologically. And the idea for why this is true is kind of a two-step idea. First of all, if you take the cubical complex and take its 0th co-skeleton, so that's the complex with the vertices deleted, you can take a deformation retraction from that cubical complex to the union of its hyperplanes. So for each cube, you can take that cube with the corners deleted and deformation retract it down onto the union of its midcubes, and do the same for every cube and glue those cubes together. You glue the deformation retractions together as well. You get this, this retraction here onto the union of the hyperplanes. And once you've got to that point, we can call on this really useful topological theorem here called the Nerve theorem, which says that if you have a collection of subspaces of a topological space, I think paracompact is the niceness condition, that's not important. And then one other condition about this collection of subspaces that you get, then the union of those subspaces is homotopy equivalent to something called the nerve of those subspaces, which is the simplicial complex that tells you when sets of them intersect each other. So in this case, this theorem tells us that the union of the hyperplanes of the cubical complex is homotopy equivalent to the simplicial complex that tells you when they intersect, which is exactly the crossing complex. All right. So to apply this nerve theorem, we do need to check this condition here, that all non-empty intersections of the spaces SI are contractible. So all non-empty intersections of hyperplanes are contractible. This follows kind of immediately from some of these properties about cat-zero cubical complexes I mentioned a couple of slides ago. So all non-empty intersections of hyperplanes in the cat-zero cubical complex are cat-zero as well, and all cat-zero cubical complexes are contractible. So yeah, applying this theorem here, this nerve theorem, is very strongly tied to these properties of being cat-zero for the cubical complex. All right, so I call this result a lemma because there's actually a consequence of this lemma that I care more about. So to kind of wrap up this talk, I'm going to tie together the two strands of ideas we've been talking about, this cat-zero cubical complex stuff, and also the theorem we had about Cohen-Macaulay and other similar properties for polytopic complexes. So to tie those together, we end up with this theorem here, which says that if X is a cat-zero cubical complex, then this complex has a bunch of properties if and only if its crossing complex has that same property. I think it's a really cool result. And the proof isn't hard at all now that we've built all of these pieces together. Here's the proof. We characterized what it means for X to have each of these properties in terms of the homologies of co-skeletons being 0 for some range of I and K. That range depends on the property, but there's some range of I and K where it's equivalent to the kth co-skeleton being 0. But according to this lemma we had on the previous slide, the kth co-skeleton of X is homotopy equivalent to the k-1th co-skeleton of its crossing complex. And homotopy equivalent spaces have the same homology groups. So we can replace this co-skeleton of X with the co-skeleton of the crossing complex. But then, kind of by magic, the range of I and K that we get from this this proof so far is exactly the range of I and K, more or less, that we need for the crossing complex to match this characterization of when it has these properties. So yeah, again, kind of by magic, we get this equivalence here. There are a couple of tiny details about edge cases here that I'm not mentioning, but apart from those details, the proof really is very simple now that we've built up all of the pieces, the rest of this talk. So there we go. Yeah, thank you for listening.
Hey, let's thank our speaker. Thank you, Rowan. I appreciate, the classic proof of, yes, the proof is simple. Once you have built up all of this machinery in the background, please, really, once you have the proof solving machine, it's a snap.
Yeah, it's always how it goes, isn't it? Yeah.
Yeah.
We'll say that there are some details, several details in the machinery that I definitely skipped over today, but
right.
Yeah.
So does anyone have any questions for Rowan?
I do. Hi, Rowan.
Hello.
So if you take the skeleton of a simplicial complex, which is really only what I know about, you're in the face lattice, you're taking everything below a certain rank. So if you take the co-skeleton, you're taking everything above a certain rank. So
yep.
How does all the poset topology machinery fit into this?
That's a good question. I haven't really considered that very much. I think there is probably stuff you can do with that. But yeah, I haven't really thought about it enough to give an answer to that question. Yeah, sorry. Yeah, I think that's definitely an interesting thing to ask, and yeah, maybe I should consider it next.
Yeah, there's just a lot of papers out there about that sort of thing. Thanks. Very nice talk. Thank you.
Thank you.
I have a quick question. So this just kind of occurred to me. So you mentioned, so the connection between a skeleton and a co-skeleton, you know, put them together, you get the entire thing. So if your original object was some kind of complex of a sphere, does that mean that there's some kind of, this is related to the Alexander dual? No.
It is related to Alexander duality. Yeah.
Okay.
Yeah, actually, in the Alexander duality, yeah, we're kind of seeing it in this picture here as well. Like this this complement of the zero skeleton, so complement of the vertices here, the homologies end up being, where did it go? Which one are we looking at? This one here. Yeah, you kind of get kind of like the homology of the 6 points that you're deleting as well. So yeah, this is definitely very tied to Alexander duality. Yeah, some of the techniques used to prove Alexander duality as well, or Poincare duality, that kind of range of results. Yeah, do kind of consider co-skeletons in a kind of roundabout way. So one thing about the co-skeleton, one disadvantage of the co-skeleton is that it is not a polytopic complex, but it is homotopy equivalent to one. So if you take the barycentric subdivision of your original complex and then delete the K skeleton of the original complex from that, you can have a deformation retraction down to some kind of like combinatorial complement of it as well. Yeah, I'm being very vague on the details here, but this kind of construction is sometimes used as a step in proving Poincare duality. Yeah, some authors have called this like the dual skeleton of the space.
Okay.
So yeah, in some sense, I'm kind of taking that idea and applying it more broadly. So Poincare duality, Alexander duality only really applies to manifolds and spheres in particular for Alexander duality, but my results, yeah, I don't assume anything's a sphere or a manifold. So
yeah, excellent.
Right. So going back to what I was thinking about, it's like you're taking the dual poset and then taking the skeleton of that. Right. You're turning the poset around. Yeah.
Yeah. I think specifically I'm taking yeah, let's say you take the dual poset and take a kth skeleton of that, and then take the what's it called? There's a simplicial complex associated to that turns out to be the barycentric subdivision. Order complex, that's the word. Yeah. Yeah. So I'm taking the dual poset and then a skeleton of that, and then the order complex.
Okay.
Yeah, which is very similar to how some proofs of Poincare duality go.
Okay, I had another question from some of the later slides. So you have this nifty little theorem that at least the proof, the idea of the proof at one level goes through the nerve. Yeah, it uses the nerve theorem. And so, yeah, it's the idea that, okay, you can think of these things, the crossing complex. So this is true for cat zero complexes. Is there any sense of, is there a bigger class of complexes this should be true for? Like, is cat zero sharp, or are there, or is just like cat zero is a nice case, but there are other complexes that should have this homotopy equivalence?
Good question. My guess is that cat zero is, if not sharp, but close to sharp. Yeah, in order to even apply the nerve theorem, you need this condition that non-empty intersections of hyperplanes are contractible, which is like very strongly tied to the definition of a cat zero space.
Okay.
If there are some ways of generalizing cat zero-ness, like if you if you take this definition of cat zero and delete the simply connected bit, for example, then you get a space with non-positive curvature, which is something people consider as well. But then the hyperplanes are not usually contractible. And so like you just can't apply the Nerv theorem. There might be some generalization of the Nerv theorem you could apply. I'm not aware of such a thing, but
Sure.
yeah,
Yeah, I
like
mean,
there
it would
might be
be,
ways that, yeah, my guess is cat zero space is kind of exactly the kind of space that you need to work with for
okay.
all of these properties.
Yeah, because the first step where, you know, the idea is like, okay, once you've punched out all the corners, then you contract down, you get the hyperplanes. It's like, okay, yeah, no, that makes sense.
That works
But
in general. Yeah, that's that.
it's the second step where it's like, and now I can use the Nerv theorem where you're like,
Yeah, this first step, yeah, that really applies to any cubical complex. Yeah, but the second step, you do need something very special about the complex.
yeah, like the Nerv theorem is broad, but it's not that, it does have conditions.
Yeah, yeah. Very useful theorem. Yeah. Yeah, I'd probably put it in like my top 5 favorite theorems.
Do we have any other questions for Rowan? Okay, well, let's thank Rowan again. Wonderful talk. And the recording's done. Oh, no, the recording's not done. The screen sharing is done.